Hey folks, this is Captain Jones here to talk to you about memory mapped output. So similar to our last lesson, we're going to describe what the circuitry is that allows us to write programs that write to a memory location and in effect write to an output device. And our objectives today are to get you to not only just describe that circuit, but be able to write short programs that talk to those output devices. Additionally, I'll present to you sort of what's kind of the other way to think of interacting with hardware. So we've been talking about memory-mapped I/O. There's another form called programmed I/O that we'll take a look at in this lesson, so you get a feel for what are different implementations or different solutions that are out there. So let's get started. Okay, so here is our model of the computer. We're going to look at the output today. We already are familiar with this idea of memory-mapped input-output, so now we've got two new places in memory, FE04 and FE06, that allow us to talk to an output device, in this case, a display. So we're going to imagine that we've got a little monitor here that has an 8-line parallel connection to our LC3, such that whatever ASCII value is written to the display data register DDR shows up on the display, and then just like our last lesson, we learned that we need to ask ourselves how do we actually synchronize with this device. So the display also has its own status register, DSR, the display status register, that gives us some useful information. You can see here that the data register, just like our input device, we're only going to use the lower 8 bits. It's assumed that the lower 8 bits are some valid ASCII character, and whatever gets written to this register is printed to the display. The DSR doesn't have a new bit; it has something called the ready bit. So the display, while it's processing some piece of data, will leave this bit cleared, and then whenever the display has read this value in the data register and is ready to receive new data, the R bit in the DSR will get set to 1. So that's kind of summarized here. Writing to the data register clears the status register, bit 15. As soon as the display reads and is done processing this character, then it sets it to indicate, hey, I'm ready for the next character. As long as this bit is cleared, then any writes to the data register are sort of silently ignored, silently rejected. So just like our last piece of code, our input code that needed to before it wrote or read from the data register, we had to check if it was ready or if there was a new piece of data. We have to do that here as well. So this is sort of the equivalent piece of code for our output device. If we're going to try to write something first, what we want to do is load the value of the status register into R0. Recall that if this bit is a 0, if we're not ready, then this value looks like either a 0 or a positive 16-bit number. So if the value of the status register is 0 or positive, then that means bit 15, the ready bit is 0. So we're going to branch to this not ready piece, and we're going to do something else in our program. If, however, this bit is a 1 and the number looks like it's negative, we're not going to take this branch. Well, instead, we know where we're ready for more data. So then we can do is store some value. In this case, we'll assume that the ASCII value we want to send to the displays in R1. We can store that value in the display data register, and then that'll get sent to the display. Okay, so here's what this looks like in implementation. So again, recall that this concept of memory has an abstraction where I have got memory values from 0 to FFFF, and I got 2 in the middle here, FE04 and FE06, that allow me to interact with the display. In actuality, I've got my block of memory here that actually stores my instructions and my data. Separately from that, I've got 2 registers, the display register and the status register, that are connected to my output device, and it is the function of the address control logic and the InMux to control, based on which address I'm writing to, whether or not the address I'm accessing is here in memory or is one of these output registers. So if we're reading from the status register to check if the display can receive more data, then that's one value that goes here to the NMUX, this multiplexer, and ultimately to the memory data register. Now we're not just reading from our hardware devices, we're also writing to them. So you can see here that the display data register gets sort of this value that might come out of the memory data register. So if something is being written to memory, it'll get loaded into the memory data register, and either, if it's an actual variable in memory, it'll go here. If we are writing to the data register, then we need this connection here from the memory data register to the display data register, and we need another control signal from our control logic to tell the data register when it's supposed to load that value. So just like before, a couple extra pieces of logic surrounding the actual memory device. Everything inside the green block includes those logic and the actual chunk of memory with our data and our instructions. But as long as we configure the control logic correctly, our processor can interact with everything inside this green box as if it were this abstraction, meaning we can read and write from memory addresses from 0 to FFFF, and we can do that successfully, and we know that FE04 and FE06 are registers that relate to our display output device. Okay, so then let's look now at something called programmed I/O, which is sort of the opposite of, well, I shouldn't say the opposite, but it's separate from MemoryMapped IO. So this is another way we might interact with our hardware devices, and so instead of accessing these registers, these output devices, as if they were in memory, what we might have chosen to do is have our address, our data, our control lines going to the memory as well as to these devices. In which case, we don't access these hardware devices as if they were in memory. Instead, we're going to have special instructions that perform reads and writes from I/O devices. This is actually how the 8085, if you recall from E360, the 8085 handles input-output. So I'm going to see if I can pull this up really quick. You might recall when we were playing around with the 8085, writing programs for it, when we wanted to read and write from our input and output devices, we had specific instructions, out and in, that referred to specific 8-bit addresses for our input and output devices. That was how we made these big circuits that addressed our devices from our 8085. So the 8085 is one example of, and actually, I'll pull one. I'll see if I can pull one of those up really quick. No, not that. This is it. Okay, so you might recall, making these big NAND gates that turned registers on and off in order for these input-output devices to put stuff onto the data bus. So this is an example. This is one kind of representation of this diagram right here. You've got your memory connected to various input and output devices. You've got your memory separate from your input and output devices. All of them are connected to the processor via address, data, and control lines. And so these three would, be connected to the processing unit in our LC3. And in programmed I/O, we have separate instructions like in and out that allow the processor to read and write from I/O devices. And so the biggest difference between these two are that if in programmed I/O, I can use all of my memory for my data and my instructions. So you recall from the LC3 ISA, right, our instruction set architecture, we have a maximum of 65K of addressable memory, right? The assumption is that however this computer is being implemented, the maximum value we can address in memory is FFFF. If I'm using programmed I/O, I can use all 65K or 64K for my programs and my data, and I can have as many input and output devices as my special instructions allow me to address. The downside is that I need special instructions, I need opcodes reserved to be able to interact with those devices, and so I might need I need some special opcodes to do that. In MemoryMapped IO, I don't have all of my memory available to me. I have the maximum sort of addressable FFFF minus however many values I need to reserve for my input and output devices. So if I jump back to one of our earlier lessons on the memory space, you can see that here. I have to reserve some amount of my addressable memory for hardware interactions, and this is memory space that could have been used by programs that were running, data or instructions, and I can't. I've reserved them for inputs and outputs. So MemoryMapped IO, eats away into my addressable memory, but because of the fact that it's that reading and writing these output devices uses the same instructions as reading and writing from memory, I don't need any special instructions. So the programmed I/O and MemoryMapped I/O both have their pluses and minuses. In the case of the LC3, we only have room for 16 opcodes, so those are very limited. But the addressable memory is 65,000 spaces, which for modern processors not much, but for lots of smaller applications like little toasters or light switches that just kind of need to run really small programs, that's plenty of memory. And so in this case, it makes sense that the LC3 would utilize MemoryMapped I/O. We don't want to eat away, 2 of our 16 opcodes just for inputs and outputs. Well, instead we'll eat the cost on our memory, which we've got a lot of anyways for at least for many applications, and that way we don't need to reserve special opcodes for MemoryMapped I/O. We don't need to reserve special opcodes just for interfacing with our I/O devices. Okay, so today we looked at MemoryMapped output. The process was very similar to MemoryMapped input, and that we have a couple of special registers here in our memory space that allow us to send data to a display and perform the process of synchronization or handshaking that allow us to know when that display is ready to receive more data. Just like our inputs, our MemoryMapped input. To actually implement that, we have some logic surrounding our actual chunk of memory here that controls whether it's the memory or our output registers that we're reading or writing from. And so then these registers here are controlled to our display device. And then we have a couple extra connections here that allow us to potentially read from the status register or write to the data register. And then we looked at the difference between programmed I/O and MemoryMapped I/O. Programmed I/O was one that we might be familiar with from EE360, where we looked at how the 8085 uses special instructions in and out to control the input and output devices. And the advantages to that were 100% of the addressable memory was available for data as an instruction. The downside was that we had to reserve a couple of special opcodes to be able to interact with those hardware devices. And in MemoryMapped I/O, on the other hand, although we lose a little bit of our addressable memory in order to reserve some spaces for interactions with our hardware devices, by virtue of the fact that those are in memory, we can use the same load and store instructions to talk with those, and so we don't need any special opcodes for MemoryMapped output. All right, that's all I got, folks. I'll see you next time.